On part 1 of my explanation of the QG height tendency equation, I discussed dividing the very long equation into 3 different terms. A, the height tendency term, B, the absolute vorticity advection term, and C, the thermal advection term. We saw that A was proportional to negative chi, or height falls. B is broken up into 2 different terms, B1, which is relative vorticity advection, and B2, planetary vorticity advection. And C was proportional to cold air advection, or C is greater than 0 when cold air is being invected into the region at the surface. We will now examine different combinations of the B and C term and their signs, and how it affects the height tendencies of the upper levels. Remember that A takes whatever form B or C does, so that if B is positive, A is also positive. And likewise for C, in systems that are either dominated by vorticity or thermal advection. For systems that have an equal amount of both, or a variation of the two, further discussion is necessary. But for the sake of this lesson, we will either be dealing with a system totally dependent on the B term, or a system totally dependent on the C term. So again, A takes whatever sign the B term or the C term has. For the B term, we will look at 2 different regions, which I have labeled as region 1 and region 2, upstream and downstream of a 500 millibar trough. We will see that B1, the relative vorticity advection term, is negative upstream of the trough and positive downstream of the trough. Whereas planetary vorticity advection, the B2 term, is positive upstream of the trough and negative downstream. For short waves and long waves, we saw last lesson that B could be approximated as either B1 for short waves, in which relative vorticity dominates, or B2, in which planetary vorticity dominates. In region 1, upstream of the trough, heights rise because B is less than 0, A is less than 0, the change in the geopotential time is greater than 0, meaning that heights rise. And in region 2, we saw that heights fall because B is greater than 0, A is greater than 0, which means that d phi dt is less than 0, and overall geopotential falls. So again, heights fall in region 2, and heights rise in region 1 for short waves. It's the opposite for long waves, in which planetary vorticity dominates. B is greater than 0 in region 1, so heights fall, and B is less than 0 in region 2, where heights rise. For the C term, we will break it up into 2 different types of systems. One which assumes westerly tilt with height, in which the low-level system, the center of the low, is to the east of the upper-level trough at 500 millibars, and another system which has easterly tilt with height, in which the low is to the west of the upper-level trough. I have labeled region 1 as the upper-level trough and region 2 as the upper-level ridge. We see that cold air advection exists in region 1 beneath the upper-level trough. This implies that C is greater than 0, which in turn implies that A is greater than 0, and heights fall. We can take another approach by saying that because the temperature is falling in region 1, the distance between heights of constant geopotential are decreasing, and in turn, del squared of the geopotential is increasing, which is defined as relative vorticity, which is also increasing, meaning that there is PVA in region 1, backing up our conclusion that heights are falling in region 1. In region 2, in the upper level ridge, we see that warm air advection exists. This means that C is less than 0, A is less than 0, d phi dt is greater than 0, and ultimately heights are rising. We can take the same approach as we did with region 1 and go in the temperature route, that because temperature is increasing in region 2, we can assume that expansion between the geopotential lines exists, and that del squared of the geopotential is decreasing, implying NVA in the region. This backs up the physical observation that westerly systems have an increasing amount of strength, because in region 1 we're seeing the trough deepening, and in region 2 we're seeing the ridge building. So the pressure gradient between region 1 and region 2 is increasing. In easterly tilted systems, however, we'll see that there is a different result. Note that region 1 is still in the upper level trough, and region 2 is still the upper level ridge. Warm air advection exists in the upper level trough, which essentially means that heights are rising and the trough is weakening. In region 2, there is cold air advection, implying a fall in the heights, and the ridge is also weakening. So the pressure gradient between the upper level ridge and trough is diminishing, and the system stacked to the east will begin to die.